We have seen that we can connect an instrument to our computer through MATLAB in one of two ways. We can either create an interface object or a device object. If we create an interface object, what we're effectively doing is opening a port which allows us to send commands in the form of strings which contain the command we want to execute and any parameters that this command requires, and also allows us to read data back in the form of text data, for instance, or binary data. The other way to interact with an instrument through MATLAB is through a device object. Let's say that using an interface object entails more low-level programming, whereas using a device object is a more high-level approach, in that we are basically using a device driver which contains functions and procedures which allow us to set specific parameters on the instruments or acquire data from them without a thorough knowledge of the instrument command set. In this tutorial, what we will be looking at will be the first method, which is communicating with the instrument through interface objects. The first step is, of course, creating the interface object itself, creating our port through which we can have bidirectional communication with the instrument. We have seen how to do this in the previous tutorial. We basically need to find the correct visa address for our instrument, and then we can simply create the interface object as shown here. Once the interface object has been created, we can click on Connect, and MATLAB will then provide us in the session log with the code which is necessary for the interface object to be set up and for the connection to be established. We can then copy and paste this code into the script, which will allow us to create the interface object and connect to the instrument without having to reopen the instrument control toolbox every time. So we've got the code in our script, which is the very first step that we have to go through. We can step through this code really quickly. You can see that I've inserted a breakpoint as I did in the previous tutorial, so we can execute each instruction one by one. So I'm just pressing F10 here to step through the code, and we'll do this really quickly. Now that we've established the connection with the instrument, we can start sending commands to it. So how do we actually send commands to our instrument? Well, you can see that we're using the fprintf command, which is often associated with writing to files. Well, it can be used to also write to objects, in this case an object that represents a port. So we are using fprintf to print or write a string to the port which represents the instrument. In this case, the string that we're sending is the *rst command, and this command is extremely useful since it resets the instrument completely. And I find that it's very important to use this command as the first command when we are running an acquisition routine. This is because we don't know what state the instrument is in. Someone may have tampered with it or may have been using it, and what we want to do is to make sure that every time we start, we know that the instrument is in a known state, its normal default state, and that way there is much less room for any mistake. You can also see that the following commands are quite intuitive. We are basically just switching off the waveforms on channel 2, 3 and 4, and then we are keeping the channel 1 waveform on. Before we carry on, let's talk a little bit about the waveform that we're trying to acquire, how it is generated and what we are using as a trigger signal. What we're trying to acquire is a pulsed RF waveform. So effectively we are using a square wave with voltage levels which are typical of TTL systems. And with this square wave, we are modulating an RF signal generator, effectively turning it on and off to generate our pulsed RF signal. The very same square wave that we are using to modulate our signal generator, we will also be using as a trigger signal for our scope. Now, the first thing that we need to do is set up the trigger for our scope correctly. We have set up the system so as to have the trigger signal on channel 1. So we need to send a command to specify this. And then we can also specify that it will be an edge trigger and that we will be triggering on the positive going slope of the trigger signal. Because we're using a square wave which is characterized by TTL voltage levels, then using 0.5 volts as a trigger level will be adequate. The next thing that we need to do is set up the scope so that we can see at least one whole pulse on the display. The way to do this is to use the pulse repetition frequency and the duty cycle of a modulating square wave and then calculate a range for the x-axis which ensures that at least one pulse will be displayed. So our modulating square wave has got a pulse repetition frequency of 100 kHz, which is something that I've decided to set the pulse generator to. And you can see that we can assign the value of 100 to the variable PRF without having to declare the variable type beforehand. This is a major advantage that MATLAB has over other programming languages because it allows you to wrap the variable around the value that you want to assign to it, rather than having to squeeze the data into a variable which you have already assigned in terms of type and size. So MATLAB is really ideal for data acquisition for this very reason. This, however, can be a double-edged sword because you always have to be very aware of what type has been assigned to the variable that you've just declared. And you may need to do some type casting as and when needed to make sure that errors are not generated. In this case, of course, PRF is assigned a numerical value of 100 and duty cycle is assigned a numerical value of 20. You can see that when you hover over with the mouse on the name of the variable, MATLAB will tell you what type the variable has been given and also what its current value is. And this is a major advantage of doing a step-by-step execution, as we've spoken about before, because it allows you to just hover over with the mouse and see what each variable has been assigned to in terms of value, but also in terms of type. The following calculation, the calculation for the variable range, you don't need to worry too much about. It's just a calculation that I worked out. It's quite simple, so that I can ensure that I will be able to see at least one full pulse. Now, PRF, duty cycle and range are all variables of a numerical type. However, when we send a command, we must send strings. So let's look into concatenating strings and the conversion of numerical values into string in a little bit more detail, since this is very important. Now, remember that strings in MATLAB are defined by quotation marks. Now, if we look at the variable date, which is assigned to the three strings, 28 December and 1976, contained by square brackets. Now, the fact that we've got three strings in there and that they are enclosed within square brackets means that we are concatenating them into one string. So the variable date will be equal to one single string, which is the union of the three that we've got in there. We could have also assigned three different variables, day, month and year, to string values. Again, remember the string values are defined by the quotation marks. In this case, MATLAB would have set the type for all the variables, day, month and year, to string, and then we could have concatenated the strings just by enclosing the name of the variables into square brackets, and this would have had exactly the same effect as the command that we had above. However, if we assigned three variables in the way which is shown here, where day and year are assigned to a numerical value, then we would encounter problems in trying to just concatenate these three variables as they are. Of course, we said that MATLAB assigns a type to each variable automatically. Now, day and year will be assigned a type double, because the values that they are assigned to are not inserted in quotation marks, whereas month would be assigned a type of string. So if we try to execute the concatenation instruction yet again by using the square brackets, this would fail. What we need to do is to convert the variable day and the variable year into strings, and then we could use these conversions to concatenate the strings as is shown here. So, based on the pulse repetition frequency and the duty cycle, we've calculated the range for the x-axis, our time base. And now we need to create a command which we can send to the scope to set the time base to the calculated value. So how do we create this command? Well, first of all, we know that to set the time base, we need to start with the string timebase:range. So we've got that one there. Then we need to concatenate that string with another string which represents the value of the range. The range is in numerical format at the moment, so we need to convert it into a string. And this can be done with the num_to_string command. So from the instruction that is used to create the string for the range command, you can see that we are concatenating a string which we already knew with a value which we have calculated. Once this is done, as we did before, we just use fprintf to write to object1 output the range command. So now we've set the range for our x-axis so that we can have at least one whole pulse displayed. However, because we are triggering at the very edge of the pulse, it may so happen that the pulse just about fits on the screen. So what I've done here is to calculate a delay which enables us to shift the pulse a little bit further away from the edges of the screen and make sure that none of it is cut off. So the calculation is again performed in a very simple way that we don't need to dwell into it. And once the delay value is calculated, by using numerical value of course, then we have to convert it from a number into a string, as is shown by the instruction here. And then we need to concatenate this conversion of the value of delay with the actual command that sets the delay. And once we've created this command, which is a delay_command here, then we can use the fprintf command to write this command that we worked out to the instrument and hence see the changes in the waveform appearance that are shown in the picture screen. So now that we have set up the horizontal scale on the x-axis, the delay and the trigger, we can move on to acquire our waveform. But before we do so, we can use two additional commands to make sure that there isn't anything that shouldn't be there in the status registers and the output buffers. And to do this, we can use two commands for this particular instrument, DCL and CLS, which will clear the status registers and the output queue. Sometimes, for some reason, it may so happen that there's something left in these registers in the instrument, and because of this, then we end up with unwanted binary data, which can mess up our acquisition. So it is certainly good practice to do this. So our trigger signal is on channel 1, but the signal that we want to acquire is on channel 3. So in a similar fashion to what we did earlier, we switch off all the channels apart from channel 3. Next, we adjust the vertical scale of the scope to suit the signal that we are acquiring. To do this, we ask the user to give us the input power that the scope will see. To prompt the user for a value, we can use a very simple classic MATLAB command, which is the input command. The first argument of this function is the string that the user will see and which will prompt him for a value. And then the second argument is the type of value that will be read in. In this case, we've specified that the type of value read in will be a string. Now the value that we read in will be put into the variable POW, and because we specified that the value read in will be a string, then POW will be assigned string as a type. At this stage I must point out that we could have also specified that the value read in was a number, and in this case the variable POW would have been given a type of double. However, the reason why I'm doing things this way is because when we use GUIs to get inputs from the user, we usually read the data in as strings, and then we need to carry out the necessary conversions. So I feel that it is more instructive to assume that we are getting the input from the user in a similar fashion as we would from a GUI. Next, we declare a variable called RES, which stands for resistance, and we set it to 50 ohms. This value is necessary to convert power into voltage in an RF system. So the user has told us what kind of power we can expect from our RF waveform. But the problem is, if we use that value to determine the scale of the y-axis, we may end up having our RF signal really close to the edges of the screen. To avoid this, we'll artificially increase the value that the user has given us by 2 dBm. This way we are assuming that the waveform that comes in has higher power than what it actually has, and hence set the y-axis in such a way as not to have the RF waveform too close to the edges of the screen. You can see that because the variable POW is a type string, we need to first convert this value into a number to then be able to carry out any mathematical manipulation, and this is what the instruction just demonstrates. So now we've calculated a value for the power, which will allow us to work out the peak-to-peak voltage of the waveform. And the next two instructions are used just for that purpose. Once we worked out the peak-to-peak voltage, then we can set up channel 3 in such a way as to have the waveform displayed correctly on it. First of all, we set the offset on the y-axis to 0, and then we select the range for the y-axis to be equal to the peak-to-peak voltage. Notice how, again, here we've got the command which consists of two parts. Firstly, the string that is used to set the range for the y-axis, and secondly, the value for the range. The value for the range, of course, was calculated from mathematical equations and hence will be a number, so we need to first convert it with the num to string command before we concatenate it with the other part of the command. And then we can send it to the instrument simply by using the fprintf command on object 1. So now our scope is fully set up. We have the right horizontal scale, the right vertical scale, and the trigger has been set. So it is time for us to acquire the waveform that we're interested in. The first thing that we need to do is send a command to specify which channel we will be acquiring our waveform from. And this is channel 3, as we said, that's where we've got our pulsed RF waveform. Next, you can see that I'm inserting a pause of 1 second. This can be very important and can make the difference between an acquisition routine working and not working. The thing is, with instrumentation, sometimes you need to give the instrument some time to actually carry out the instruction that you've given it. For example, if you want to set a specific parameter to a specific value, this may not happen instantaneously, and you may need to give the instrument just a little bit of time, particularly if it's an old instrument and if switches and relays are being used. Now, you may wonder how to work out how long you need to give your instrument and how to work out whether you do or don't need a delay. Well, this is quite simple normally. If you run your routine and errors are generated, and then you switch to running your routine step by step, and there are no errors generated, that means that you have to insert delays in some places to be able to have the acquisition working correctly. So if you get inexplicable errors, always run the code step by step, and if you don't get the same error, this means that you may need to insert specific delays to allow the instrument to set the parameters that you've asked it to set or execute the commands that you've sent. So we specified that the waveform source is on channel 3, and then we have to specify the waveform format. You can choose different levels of precision. For instance, you can choose byte or word if you want higher precision. But for the first part of the acquisition, we'll just set it to byte, since this is sufficient. Now, there are two things that you need to do. First of all, you need to get all the sampling points along the x-axis. You don't need to get a full vector of values for the x-axis because the points on it are spaced by equal amounts. So all you need to do is find out the spacing of these points and then find out where the first point is, the first point along the x-axis, the origin of the time axis. So to do this, we first send the waveform :increment command, followed by a question mark. This is an inquiry, which is clearly signified by the question mark, so we are asking the instrument to send data back to us. And this data will be the distance in time, the time interval, that separates each point on the x-axis. We can then use the fscanf command to read from object 1, which is our instrument, the floating point that will represent this time distance between the points on the x-axis. Fscanf is very similar to fprintf in the way it works. You have to give it a file identifier or an object, in our case object 1, and then also you can give it a type specifier so that fscanf knows what to convert the bytes that it reads into. In this case, we know that it will be a floating point number, and hence we use the %f specifier. We then do the same for the value of the origin of the x-axis, and hence we send the inquiry waveform :xorigin ? And then we again read the floating point number back from object 1, which represents our instrument. Now, when it comes to the y-axis, things are a little bit different. There is a different level of precision required, and hence we need to first set the waveform format to word. Then, in a similar fashion to the x-axis, we will have to work out the origin of the y-axis and the distance between the various sampling points on it. Of course, this distance will be constant. So we send an inquiry by saying waveform :y_increment ? And then we can read back the data. You can see that in this case I've used fscanf on object 1 without a type specifier. This can be very useful sometimes, because you may not be absolutely certain of what sort of type of data you will be getting back. So if you just use fscanf without a type specifier, you'll read back an array of bytes, which will be stored in the variable y_inc as an array of char type values, and then you can carry out the conversion into the numerical data type that you require. This can be very useful if you're not entirely sure of what you will be getting back from the instrument, because this way you can acquire the data and that's stored into your variable y_inc, and then if the conversion into anything should fail, you have control over that. You can go back and verify what error was generated and just check what's going on. So it's just another way to do things, another option that you have, and I'm just showing it so that you are aware of what different techniques can be used to acquire data back from an instrument. So we've acquired the value for the interval that separates the sampling point on the y-axis, and then we can get the y-origin value in a very similar fashion. So now we have all the elements that we need for the x-axis. We just need the origin and the distance between the sampling points. When it comes to the y-axis, although we have the distance between the various quantization points, we have to now get the actual data for the specific waveform and then combine it with the y-increment and y-origin data in such a way as to reconstruct our waveform. So to do this, we have to go through a specific procedure. The first part of which entails sorting out the byte order for the data that will come through. Earlier we set up the waveform format to word. Word is 2 bytes, so we have to specify which one comes first. And the following instruction is just used for that purpose. We're saying that the least significant byte comes first. Now we need to have a little bit of a digression and talk about the fread command, which we will be using quite a lot in the rest of the acquisition script. This is a very versatile command, and it just reads binary data from a file or a port. So if we just used it as shown here, by just saying fread from S port, Fread would get all the data that is available from the specified identifier into the variable ID. But we can also use Fread in a more specific way. For example, in the instruction shown here, we are saying that we want Fread to go to object 1 and read 20 values of type int16. Because int16 comprises of 2 bytes, then in actual facts we will be reading 40 bytes. We can also, for example, use Fread to read just one value of type char from our object, as is shown in the instruction here. In this case, because char is just 1 byte, we'll be reading just 1 byte. And this is very useful because sometimes this is just what we want to do. We want to go through the data byte by byte, and based on what we get, then we can work out what to do with the next byte of data. Now, before we go ahead, let's talk a little bit about the specific waveform format that we will be getting from this instrument. Each instrument will have a bespoke waveform format which the programmer must be aware of in order to be able to interpret the data that is read back in the correct way. For the Agilent Infinium scopes, and also for other instruments, the waveform format is shown below. It isn't the easiest thing to explain, and things will probably become clearer once we go through this worked example. We will have a number of bytes which will represent waveform data. So let's say that the number of waveform bytes is L. And you can see here we've got them represented as bytes in a range between 0 and L-1, which adds up to L bytes. So we need to figure out what L is. Now here comes the tricky bit. The variable L is not represented by a floating point, for instance, or an integer value, but it is a string. So we are representing a number, the number L, with a number of characters, each of which represents a digit. So for example, if the number of bytes was equal to 512, then the variable L would be represented by 3 bytes, the first of which would be the ASCII equivalent of the number 5, the second of which will be the ASCII equivalent of the number 1, and the third of which will be the ASCII equivalent of the number 2. So, starting from the end, we get 512 bytes which represent the waveform data. Then we have 3 bytes which represent 3 ASCII values, each of which is a digit of the number L. Now, this type of format is just specific to the manufacturer. You have no control over. You just have to accept it and deal with it. So we said we have L bytes of waveform data, 512. These are preceded by 3 bytes, which are the ASCII values for the digits 5, 1, and 2. Now, this string of digits is preceded by another number, the number n, which tells us how many digits there are in the string which represents L. Because, of course, we will be starting from the very beginning of the chunk of data, and we need to know how many digits there are in the string representing the number L so that we can work out when the actual waveform data starts. So now, looking at things from the beginning of the chunk of data, we will have a hash character which represents the start of the response. Then we'll have one single ASCII value which represents a digit, and this digit represents the number of characters in the string L. So in this case, n would be equal to 3. So now we've been told that we have 3 digits in the string L. Then we can move on, read 3 bytes, because we know that the variable L is represented by a string of 3 characters, and then we can convert that string into a number, work out how many bytes there are to follow, and we know that those bytes will represent waveform data, and we can read those in. So let's crack on with the script and see if we can make this any clearer. So the first instruction that we send to the instrument is digitize channel 3, and this basically digitizes all the data and stores it. Then we request this data with the command waveform::data ? And we'll get the first chunk of data, the format of which we've just looked at, back into the PC. So now what do we do with that? Well, the first thing we do is we try to find the hash character, which is the start of the response. Don't assume that the first byte that you will read is the hash character, because for some instruments the hash character is preceded by the instrument name or some other settings, and hence don't just assume that. You can set up a simple while cycle like I've done here, which will carry on reading bytes and discarding them until you find the hash character. Once you've found the hash character, you know that you are at the start of the response, and you know that the next byte that follows will be a digit in ASCII format, which will give you the value of the variable n. So we read in an extra byte of data by using this instruction, and we assign this byte of data to the variable header length in ASCII. So we've read in an extra byte, and this byte represents an ASCII value, and this ASCII value in turn represents a digit, and this digit, once converted into a number, will give us the value of the variable n. So you may think that we could just use the string to num function to convert the variable that was returned by the fread instruction into an actual number. However, when we hover over with the mouse on the variable that was returned by fread, header length in ASCII, we can see that the type that was assigned to this variable is a type double. So you can see that in this case, although we have specified as one of the parameters of the fread function the specifier char, this has actually served the purpose of us reading the right size of data. So reading the number of bytes corresponding to a one ASCII character. But although it gave us the right size for the data, it did not return a data type which was that of character. It actually gave us a type double. Now the decimal number, which is contained in the variable of type double, is still correct. It represents the right ASCII number, but we can't use the string to num function to directly convert it. We have to first typecast it. And there is a simple function that allows us to do that called char. So we can use char on our variable header len ASCII so that we can convert the decimal value, which at the moment is stored in a variable of type double, into an actual string value or character value. And then, since char returns the right type of value, which string to num can handle, the instruction that is shown here will work and will give us the correct numerical value corresponding to the one that we read in with the fread instruction. So now we know how many digits there are in the string that represents our header length L. So we can just now read that many values of type char, or that many bytes, from the first chunk of data that we got, and this will give us the string which represents the value of the variable L. Now there are a couple of little quirks again that we have to look at. We have read in n values of type char. In our case, n is 6. But as you can see, fread returned an array of 6 values, but each of these values is of type double. So just as we did before, we'll have to convert this array of values of type double into an array of characters. And we can do this just as we did before with the function char. You may also notice that we have a column vector rather than a row vector. And this is normal, is what fread returns. When it reads more than one value, the values will be stored in a column vector. However, the string-to-num function will not operate correctly if we pass a column vector to it. It's got to be a row vector. So basically we need to do two things here. Firstly, we need to convert this array of values of type double into an array of values of type char, and then we need to find the transpose of this vector so that we can turn it from being a column vector into a row vector. And then we can use the string-to-num function to convert this string into a number. And this number will represent L, which is the number of bytes which the entire waveform comprises of. So now we know just how many bytes there will be in our waveform overall. But we can't acquire all this large chunk of bytes in one go. When we invoke the command waveform::data?, the output buffer of the instrument is filled initially with the waveform header and then the first set of the waveform bytes up to the maximum size of the output buffer. This means that then we'll have to go through a number of iterations to get all the rest of the data. The size of the output buffer of the instrument may be identified by looking at the size of the input buffer of the object which represents the connection port. And this parameter can be accessed easily by using the dot notation. So to work out the bin size, the maximum number of bytes that the instrument can provide at any one time, we can just declare a variable called bin_size and assign it to the input buffer size property of object 1. So now we know just how many bytes we're going to have in our waveform data, which is given by the variable L, and we also know how many of these bytes can be made available at a time by means of the variable bin_size. So the number of iterations would be the number of bytes in total that a waveform comprises of divided by the bin size. So let's now go back to the script. So we have to declare the bin size variable as we've shown before. We can work out the number of iterations as L divided by bin size. Then we need to approximate from above the number of iterations to the next integer as shown by the instruction here. This is to ensure that we don't miss out any of the data. And then we have to go through a number of iterations, and in each iteration we will read the maximum number of bytes that we can possibly read from the output buffer of the instrument, which is signified by bin size. Now when you look at the iteration code, you may wonder why when I use Fread I ask it to read a number of value equal to bin size divided by 2 rather than bin size. And this is easily explained. The thing is, each element in the waveform will be a word which comprises of 2 bytes. So it is easier for me to actually read 2 bytes at a time because they represent one value rather than read 1 byte individually. So what I'm asking Fread to do is to read 2 bytes at a time by specifying the type of value as int16, which comprises of 2 bytes. And because I'm reading values which comprise of 2 bytes, then the number of values I need to read is bin size divided by 2. This adds up to a number of bytes equal to bin size. So once we've gone through all the iterations, we will have all the waveform data stored into the array A. In order to then reconstruct the actual data for the waveform, we'll need to work out how big this array is. And to work out its size, we can use the size function. However, we have to be very careful with this type of function because, for example, if we have a one-dimensional array, the array x shown here, and then we pass it on to the function size, size will return 2 values to say that we have a 1 by 5 array. So to make sure that we get the maximum dimension of the vector that we're trying to work out the size of, we need to use the max function combined with the size function to make sure that the value returned is the maximum dimension of the array that we're interested in. Alternatively, we could have used the length function. So now we need to be able to recreate the actual values for the x and y axis of our waveform. For the x-axis, this is very easy. We start from the origin and then add a number of points up to the full range, which are at a distance equal to x inc. For the y-axis, this is not as straightforward. We've got all the quantization points and then the data that comes from the instrument, and we have to use a formula to reconstruct the actual voltage waveform for the y-axis. So once we've done our for cycle, which of course has to run for the number of elements that we've got in our array, we can then plot the data or store it in a file, do whatever we want with it, now that we've got the two variables for the x and the y-axis data. And then, of course, we have to remember to always close the object which represents our instrument.